What about at a different location? Let's, in fact, ask a question about this. So we know the electric field inside the capacitor, and we're not showing the whole discs here, but you get the idea. One's positive, one's negative. Here's E inside. Here's a little location. This little green X here is outside of the gap. Okay, so it's outside of the negatively charged plate here. Which arrow best represents the electric field at that little X? Think about it. Talk to your neighbor. Okay, so biggest answer is 4, which is kind of pointing toward the negative plate, right? And that's probably a good expectation, because if we are at a location here, we are looking at, again, the superposition of two electric fields. The electric field due to the positive charge is pointing in which direction? That way. Electric field due to the negatively charged plate is pointing that way. And which one's bigger? Field due to the negative, right? Now you might say, well, how many people actually went for 3? Not many. Okay, 4% said 3. Didn't we just get done saying that the electric field is uniform? Well, we're starting to get farther and farther away, right? So that field being uniform approximation might not be a very good one when we start to get far away, particularly farther away from this positively charged plate. So we might have to go back to thinking about looking at the electric field of a disk using maybe the formula Q over A over 2 epsilon 0 times 1 minus Z over R. So we end up with a electric field that's going to be a net electric field pointing that direction when we do the superposition. And let's see if we can work out what the magnitude is. Same idea. The net electric field is going to be the electric field due to the positively charged plate plus the electric field due to the negatively charged plate. And I'm just going to look at the component, the X component. And, okay, they're calling this Z, but don't get confused by that. The Z distance is just along the X direction in this particular case, so don't worry about that so much. Okay, so the X component would be, we have the field due to the positively charged plate is going to be pointing in the positive X direction. So that would be positive Q over A over 2 epsilon 0 times 1 minus the distance from this point to this point. Well, what do we want to call that? Let's see. This distance is S. Let's see. Yeah, let's just call that distance Z. All right, so let's call that distance Z. Even though it's along the X direction, it's okay. So this will be 1 minus Z over R. And then we have the electric field due to the negatively charged plate. So we have the field due to the negative charge is pointing in the negative X direction, right? So it's going to have a negative X component. The Q here, I'm just saying, is a positive number, so this is Q and this is negative Q. Q over A over 2 epsilon 0. I have 1 minus, now what's this distance? What is the distance from this plate to this observation location? If this is S and this is Z, then this distance is what? Z minus S, right? Okay, so we have 1 minus Z minus S over R. And if you work this out, let's see, we have, what are we going to get? We're going to get some things canceling out. The Q over A over 2 epsilon naught minus Q over A over 2 epsilon naught. That's so essentially that factor of 1 and minus that factor of 1. We have minus Z over R Q over A over 2 epsilon 0. We have, if we bring the negative sign inside, we have a plus Z over R Q over A over 2 epsilon 0. And we end up with a minus S over R Q over A over 2 epsilon 0 when we work out all the algebra. So a lot of things cancel out here. That cancels out. That cancels out. We end up with the X component. I'm just going to look at the magnitude here. The magnitude of the field of a capacitor outside the gap on the center axis. Q over A over 2 epsilon 0 times S over R. This depends on the geometry, or depends on the area. It also depends on the size of the gap. The bigger that gap, the bigger that field is going to be, because you have a less of a more of a difference between these two fields, and you get less cancellation. Okay, if I squeeze these two plates together, that S gets smaller and smaller. These fields get closer to looking more identical to each other, and this gets closer and closer to 0. This thing is called the fringe field of a capacitor. So it's the field outside of that gap. It just has a special name, and we'll be using that occasionally through the semester as well. Okay, so we're almost done with deriving all these sort of special case results that we're going to be coming back to. And there's one more that we have talked about that we didn't get really a chance to derive, and I'm still not going to formally derive it, but I'm at least going to show you where it comes from. And that is the field of a uniformly charged sphere. So here's a positively charged sphere that has a uniform charge distribution over its surface. Uniformly charged, or uniformly distributed charge on a sphere. Outside, what's the electric field look like? What do we use for the magnitude of the field outside the sphere? Anybody remember this? You had to use this result in a homework, I think. It looks just like the field of a point charge, right? What's the R? The R goes from where to where? From the center of the sphere, right? So you can sort of treat it like a point charge at the center, and it behaves exactly the same way. Okay, so outside, it's just 1 over 4 pi epsilon 0 Q over R squared. Inside, the electric field due to that charged sphere is what? Anybody remember? It's 0, yeah. End up with the electric field due to the sphere. Not necessarily the net electric field, because there may be other charged objects outside that may make electric field at that location. But the field just due to that charged surface gives you 0. How's that work? Well, essentially we do the same thing. We break it up into pieces and add them up. And the pieces that you want to break it up into are actually rings. And let me show you a little program that gives you an idea of how this works. Here's our uniformly charged sphere. I'm going to break it up into rings by slicing it up kind of like latitude lines on the globe from one pole to the other. So there's ring number 1. And since that's kind of hard to see, I'm going to take the surface away and just look at the field due to the ring. Okay. So I have here the field due to one ring, the delta E, and the running total of the total electric field due to all the rings. Here's the next ring. It makes a delta E pointing away from it along the axis, just as rings do, positively charged rings do. The next delta E, and so the green arrow is the delta E, the orange arrow is the running total of the electric field, adding up all the delta E's. And so we get a larger and larger electric field until we get to a point where we're right on the axis, okay, or we're right on where our observation location is right in the center of the ring. That delta E gives us approximately 0. Go one step past that delta E, or that observation location, and now the electric field due to that ring is going to be pointing in the opposite direction. It's a little bit hard to see here, but that green arrow is pointing now to the right instead of to the left. Keep doing that, and if I zoom in here, we see this delta, this E of the ring gets getting bigger and bigger in the opposite direction. I keep adding that to my running total, and that running total keeps getting smaller and smaller and smaller because I keep adding up more and more electric fields pointing in the opposite direction. When I finally reach the other side of the sphere, it actually does add up to be equal to 0. And you can do it analytically, and it's worked out in the end of the chapter if you want to actually take a look at it. We won't go through it. But it actually does really, really work out to be 0 inside. Okay? Next time we will start something new.